Okay, so let us continue with the last part. We stopped at this portion when we were discussing about the computation of the service entrance or the size of the feeder. So here we get the total summation of the total currents, load currents of each of the branch circuits, and then of course we have to add 25% of the biggest motor load there, whatever is that, the value of that, you have to add it. And then of course if you want to make your service entrance fully has the capacity, you can just use this total as the basis of sizing the service entrance wire. So in this case 38 mm THN is selected, and 22 mm squared is the size of the ground wire. Okay, and the circuit breaker must be selected exactly to protect the selected service entrance wire. Okay, it is also possible to, it is also allowable to use a demand factor. Say for example 80% is very much widely accepted as a demand factor, and that will make your service entrance wire smaller, a little smaller, but still allowed, as long as the size of the circuit breaker will exactly protect the service entrance wire. Okay, take note that we are using here THN insulation. Until today, THN wire, that means thermoplastic, heat resistant with neoprene, but it's also equivalent to the same with the THWN. It has a 90 degrees centigrade temperature rating, much higher than the THW, which only has 75 degrees centigrade, and TW, which only has 60 degrees. Okay, so next slide we show here the difference between the 3-phase 4-wire plus ground system and the 3-phase 3-wire plus ground system. So in the 3-phase 4-wire you usually have two voltages available, which is the 400 volts available from line to line, and 230 volts available from line to neutral. So in the other one, the 3-phase 3-wire system, you only have 230 volts for the line to line voltage. The line to neutral voltage is not present because you only have 3 phase lines, and no neutral line. Of course, both of these two systems have a ground, which is standard. And okay, going to the 3-phase 3-wire system, which is standard, could be 230 volts for residentials or offices, and 460 volts mostly for industrial plants or manufacturing plants. So the line current is equal to square root of 3 times the phase current. Okay, there are 4 wires, A, B, C wires, and the ground wire. Now the 4th wire is the ground wire, and there is no need for the neutral wire. In the 3-phase 4-wire system, the line current is equal to the phase current, so there's no need to multiply it by square root of 3 when getting the total line currents. So we have 5 wires, A, B, C, and neutral, and the ground. The 5th wire is the ground wire. The neutral wire is usually sized the same as the phase wire. So your size, the size of A, B, C, and N or neutral are all the same. So here we see a 3-phase load schedule, and in our example we have 6 panels, LP1, LP2, LP3, 4, 5, 6 now. So LP1 and 2 are connected to phase CA, and LP3 and 4 are connected to phase AB, and LP5 and 6 are connected to phase BC. We have to make the arrangements as much as possible so that the total currents of each phase will be almost the same or very close, or the difference between among the 3 would be the smallest. The allowable would be as much as 1%, but in case you cannot really come up with it, just do the most closest possible balancing. Okay, then you get the highest value here. In this case, it's 210 for phase AV, multiplied by square root of 3 because this is a three-phase 3-wire system. Then you add 25% of the biggest full load, biggest current of motor current, and then you add it. Then 365 will be the basis to select the service entrance or the feeder for this panel board, which is selected at 3 wires of 250 mm squared with a 125 mm ground. The positive of the wires 400, and therefore we select a circuit breaker of 400 ampere trip, 400 ampere frame, 3-pole, 230 volts circuit breaker. If this panel is a line to neutral panel, meaning 400 and 230 volts system, then this would become A to neutral, B to neutral, and C to neutral, and there will be no need to multiply by square root of 3, not in this case now, for incising the service and transfer. Whatever will be the highest among the 3 in a 3-phase 4-wire system with a neutral will be the basis of sizing the feeder to the panel. Okay, here we notice this is a graph from a blueprint drawing in a single line, where you see that it uses 8 sets of 380 mm THM, but notice the circuit breaker that protects this feeder is 1600 ampere trip or 1600. Now using 8 sets of 80 mm is not a good option, because since the 80 mm wire is not so thick, then there is a possibility that when cutting the wires, they might not be of the same lengths, and if they are not of the same lengths, then the possibility of creating circulating currents between the wires may happen. So the suggestion is, instead of using 80 mm wire, 250 mm would be much better. So it would be 4 sets of 3 250 mm. So it's the same. The circuit breaker can be selected at 1600 ampere trip. Okay, voltage drop. It is very important to calculate for the voltage drop. Okay, and this is a very simple formula to easily determine the voltage drop. Okay, 2KLI divided by the circular mil for single phase circuits, and for 3-phase circuits it's the same formula, except that you have to multiply by 0.866 or square root of 3 KLI divided by the circular mil area of the wires. Okay, so this is a very fast way to determine it, but anyway, we'll be having with another lecture on voltage drop calculations in conjunction with short circuit as well as the complete design analysis. So this is the reason why, very simple reason, that a deep well, which could be with a depth of say, for example, 20 lengths of 20-foot pipe, and that would be equivalent to about 400 feet below the ground, therefore that very deep well, depth of the deep well, will have a very long feeder up to your panel board or breaker. So in most plans, we just do indicate in the plan where the location of the deep well is, but we do not really indicate how deep the motor is or the pump is. So very important, therefore, if you do not consider voltage drop in sizing the feeder, if the voltage drop is too big, then if the system is 220 volts, if the voltage here is has become, say, 180 volts or 160 volts, then the reduction in the voltage will create high starting currents or running currents, and therefore it will make the life or the operation of the motor, the deep well motor, not good. No, will have a shorter life, because every time it starts, the starting current is high, and also the running current is also high, so it reduces the life of the deep well pump. The correct way is to determine the real depth, compute for the voltage drop, compensate for it by using a larger size of feeder wire. Okay, a fast check of the short circuit current of a transformer is to just simply use this formula. Short circuit current is equal to kVA rating of the transformer divided by square root of 3 divided by the voltage rating divided by the impedance of the transformer and times 100. But anyway, we'll be having another lecture on this, as I've mentioned already. Okay, lightning and surge arresters for power generating station as well as substation. It is very important that lightning arresters must be installed on the terminals of transformers. No, take note in this transformer that there are no lightning arresters installed there in the primary and the secondary side of the transformer. Most possibly the arrestor has been installed in the substation frame structure. No, so but the best way to provide surge or lightning protection to a transformer or to a device equipment is to install it within 3 to 4 meters away from the terminals, or as much as possible close to the terminals or to the winding of the transformer. So there should be a lightning arrestor here and also on the other side. And also you have to select the correct capacity. For big transformers, you have to use station type. And the lightning, the distribution type transformers, you can use the distribution type, the small ones. No, but the big transformers must be big ones. Okay, and yeah, this is the 3 to 4 feet requirements distance of the arrestor to the terminals or to the windings of the transformer. Okay, here is a slide that shows you how you could convert an ungrounded system into a grounded system. So if these lines here are ungrounded, no, so you can install a grounding type transformer, or yeah, here is the secondary of this ungrounded system. So you can install a grounding transformer which looks like this, Y in the primary and delta in the secondary, and the neutral point of the grounding transformer should be solidly grounded to ground, and the capacity of this should be at least 10% of the rating of this. No? So for example, if this is a 1000 kVA transformer, then this capacity transformer should be at least 100 kVA. Okay, in the absence of what you call this, a three-phase grounding transformer like this one, you could use 3 single-phase transformers. No, 3 single-phase transformers. In the case, like I said, 100 kVA is required. You should use at least 3 units of 37.5 kVA transformer, step-down distribution type transformers, with the primary connected in Y and the secondary connected in delta. Now, if it is a 5000 kVA transformer, then you need at least 500 kVA, so equivalent 3 units of 167 kVA would be required. So this one needs 10% capacity. Okay, this slide shows us the common electrical items that are neglected in housing projects. We had an inspection recently in a housing project elsewhere, and we found out that this locus housing, most of the contractors would miss several important items. Number one, the approved branch and approved samples, they do not submit to the project management for the correct one of these, so GenCons or owners or consultants should ask for approved branch or product samples. Number two, here we discussed earlier in one of the earlier parts of this seminar, bolt-on main circuit breaker should be used instead of the plug-in type. Number three, as much as possible, color coding of wire should be adhered to. Number four, grounding, because in the electrical cooperatives, they have this line to neutral or line to ground system. They miss providing the grounding system. Sometimes their convenience outlets or the outlets that they use are two-prong type only, doesn't provide for the grounding type. Okay, and number five, they usually miss making complete electrical test before energization of the houses or homes. So again, we remind those electricians or contractors, electrical contractors, to adhere to these minimum requirements to make sure that their housing projects, locus housing projects, would at least be at par with the standards. Okay, thank you very much. That is the end of our presentation. Hope you were able to pick up some things in this presentation. Thank you, and good luck to everyone.